All right, now we're going to talk about numerical data. Now, numerical data, as a reminder, are things like weight, height, temperature, things that we measure with numbers rather than words. And so often when we're displaying numerical data, we're displaying how often different numbers occur. So the most basic type of numerical data is dot plots. Dot plots are also called line plots, and they're very similar for pictographs except that the categories are numbers. So in other words, each dot means that number occurred once. So this dot right here represents some time when someone scooped up a bunch of peas and there were 18 of them in a teaspoon. This one down here represents a time someone picked up 16. So each dot is an occurrence of that number. So the number 18 occurred 1, 2, 3, 4, 5, 6, 7, 8, 9 times. Now, we occasionally also use dot plots like this, where each category could also be a range of numbers. So in other words, this dot right here represents one city that had a temperature between 0 and 9 degrees. Each of these dots here represents a city that had an average January temperature between 30 and 39 degrees. So you could call this a binned dot plot, where we've taken the numbers and sorted them into bins. Now, there are two other ways we sort them into bins. One of them is with a stem and leaf plot. With a stem and leaf plot, the bins are the tens. So let's talk about what this means. So the numbers on the left represent the tens place, and the numbers on the right represent the ones place. This is actually the same data as in the last dot plot. So this can show ranges and exact values at the same time, but it can be a little bit confusing to read. Let me make sure we know what each piece means. So let's look at, this 4 right here in the 5 row. That 4 represents 54. And this 2 right there represents 22 because it's in the row of 20s and has a ones place of 2. So we usually use this where the left-hand side is the tens and the right-hand side is the ones. You'll also occasionally see these done with different place values with decimal points, but this is the most common. Now, one of your homework problems asks you to take a stem and leaf plot and write out all the numbers, so we're going to practice doing that. So this first row is the 0 row, or in other words, the places with no tens. So that just means there's one city with a temperature of 7. The 4 and 8 represent a 14 and an 18. That means there is a city with an average January temperature of 14 degrees and one with 18 degrees. The 20 row gives me 20 because of that 0, a 22, a 26, and 29. So each of these digits represents a different number. So notice I can see real easily here that the 30s are the most common. I have 6 digits in there. And I can also see exactly where those fall. I know I had 2 30s, a 31, a 33, a 36, a 38, and I can do the same for the other numbers. In my 4s, I have 40, or sorry, in the fourth and the row starting with 4, I have 2 40s because of the zeros, 43, 44, 45, and so forth. Now, let's show how we can use this data to create another type of binned display called a histogram. Now, to build a histogram, we first need to build a frequency table. A frequency table is where we take a range and we say how often does that range occur. Sometimes we start by tallying, sometimes we can count them up, and we call that the frequency. So this is the temperature data from that stem and leaf plot. I can see that there's one number between 0 and 9, it's that 7. Between 10 and 9, there are 2 of them. 10 and 19, excuse me. Between 20 and 29, there are 4. Between 30 and 39, there are 6. Between 40 and 49, there are 5. Between 50 and 59, there are 4. And then we have 2 in the 60s and 1 in the 70s. That's the frequency. That's how often they occur. When we talk about relative frequency, that's not how often you see your ant. Relative frequency is a percentage or a decimal out of the whole. So we have 25 data points, so the relative frequency of temperatures between 0 and 9 is 1 out of 25, or in other words, about 4%. These are used if for some reason it makes more sense to talk about a percentage or it's more helpful. And you just find that out by dividing frequency over total. So let's see, this ends up being 8%, 16%, 24%, because these are all out of 25. Each 25th is 4%. So we have 20% here, 16%, 8%, and 4%. So we will use a table like this to create a histogram. So here's the histogram from that data. Notice here I have my 6 numbers that were between 30 and 39. That's represented by a column of height 6. Here I have my 4 numbers, my 2 and my 1. Here there are 5 numbers. Then the 4, the 2, and the 1. So we can think of it as our dot plot where the dots were melted together. Now this may look a lot like a bar graph. Well, a bar graph is used for categorical data and a histogram is used for numerical data. Additionally, in a bar graph, there's a gap between bars while there's no gap on a histogram. Now, a couple things I want you to notice. First, the y-axis is either frequency or relative frequency. Now, for this to be a good histogram, your y-axis needs to start at 0, and the width of your bins should be the same. So in other words, it's not like I have one bin or like one of these bars that represents numbers between 0 and 20, and then the next one's between 20 and 30. The width should be the same for each bar, and in this case it's 10. Each bin is 10 apart. Now, just so you can see it, here's a relative frequency histogram. Notice it looks almost exactly the same as the normal histogram. We just changed our y-axis values to be decimals or percents. All right, here is a line graph. Now, this is not a very good line graph. Why? Doesn't start at 0. This is a big no-no. But a line graph is used to show a trend of some sort. So here we have average math scores in different years. And the connecting line should have a meaning. So if I were to look at, say, right here on this line, I should say, oh, that's somewhere in the year 1980, they had a score around the same as 78 and 82. oh, this means somewhere between 1986 and 1990 we had some improvement, and so on. However, here's a really bad line graph. And I've seen a couple of these recently and they drive me bonkers. Notice the line doesn't mean anything. It doesn't make sense to have a line going from Georgia to Washington. Like, what does this point right here mean on the line? Absolutely nothing. So line graphs should only really look at change in a number over time.